Okay, so today we are going to talk about voltaic cells. And the reason why is because they have a lot of applications. So if you saw Breaking Bad, one of the first season, I believe, there was an episode where they were like out in the desert, and Walter White had to like use pennies to start the RV or something like that. It's been a long time, guys. That was an application of redox, and that's what I really want to talk about, is the applications of redox. Okay, so we're going to talk about electrochemical cells. And here's the most important one. The most important one is a voltaic cell. Okay, so a voltaic or galvanic cell. Basically, this is like a large scale, and if we were in school, we'd actually make them, and then we would, it's basically taking a redox reaction. So we talked in our last video about how you can't have oxidation without reduction, and you can't have reduction without oxidation, because one is the gain of electrons and one is the loss of electrons. But you can separate them into two separate containers, right? So let's say that we have, the oxidation happening in one container and reduction happening in the other container. Now remember, oxidation is loss of electrons, reduction is gain of electrons. So if I connect these two containers, I can actually get the electrons that are lost in this oxidation container to transfer to the electrons that are gained in the reduction container, okay? And when I have electrons moving, I have moving charged particles. That means I can conduct electricity. So what happens is this voltaic cell is essentially a battery, which is really cool, okay? It's actually going to generate electricity just by the differences that we have going on here and separating that oxidation and reduction. So here is a chunk of metal, and here is a chunk of metal. Let's call this one copper, and let's call this one silver, okay? Now, all things like if you've taken digital electronics, all of those things still apply. So you need to connect them with a wire, okay, like a copper wire. It doesn't matter what it's made out of, but a metal wire. And then you need to complete the circuit somehow. So here's essentially what's happening. We're going to put these in an electrolyte solution. Usually I like to put them in a solution of their own ions, right? So I'm going to have copper with some copper ions and silver with some silver ions. Now I obviously can't just like make silver ions. I have to have like silver nitrate or copper nitrate, but we only care about the cation side, so that's what we're going to pay attention to. So over here, I've got oxidation happening, and that means that the copper ions are the copper atoms here, right? This is copper with an oxidation state of 0, and this is silver with an oxidation state of 0. So in order to be oxidized, those coppers have to lose electrons. So in order to lose electrons, those copper atoms on that big chunk of copper essentially here are going to be jumping off into the solution, right? And they're going to be going from copper 0 to copper +1, because that indicates loss of electrons. Now where are those electrons going to go? They're going to go through the wire. When you have electrons traveling through a wire, you have electricity. So both of my kids have flashlights, and there are batteries in those flashlights. The lights light up, not because they're plugged into the wall, but because there's some sort of chemical reaction generating electricity, and that's what's happening here. So I have a transfer from chemical energy to electrical energy, which is really cool. So energy is still conserved, right? But it's just transferred from chemical to electrical. Now, if you've taken digital electronics, you recognize that this can't happen like this, okay? You have to connect to the circuits, right? A circuit is a circle or a cycle, and I don't have that going on here. So there's got to be more that's going on. So my copper is losing electrons. The electrons go through the wire, and then they come over here to the silver chunk. Now, what happens here is these silver ions in the solution gain those electrons, and they plate onto the silver electrode, okay? And this is the cathode, and this one, the copper one, is the anode, but it doesn't really matter for you guys. But that means it's going to gain mass, because the silver ions in the solution are going to attach themselves to that silver cathode, which is really, really cool. So they're going to gain the electrons. Now, again, our circuit's not complete, so somehow we have to connect these, and we usually connect them with what we call a salt bridge. And if we were in class, what we would do is we would take a piece of like string or like kite string, and we would soak it in like salt water. So you would have moving charged particles. So it might be, it doesn't have to be NaCl, it can be any salt, but it's got to be aqueous so that you have moving charged particles. And what that means is that your negative electrons are traveling through the wire, and they're going to come over here. And now I need to allow, as I add a negative electron to this half cell over here, this reduction half cell, I have to have negative, which would be Cl minuses, going this way to kind of complete the circuit, okay? And as I'm adding negatives to this guy over here, my positive NAs are going to be going into there to keep it neutral. So that's the salt bridge just kind of keeps neutrality and completes your circuit. What really matters is this whole process. I've got a redox reaction happening, I've got copper being oxidized, and I've got silver ions being reduced to silver metal. So I'm essentially plating silver onto this chunk over here, and I'm taking this copper metal is kind of disintegrating into, excuse me, these copper ions here. So the concentration of the copper ions here are going to increase, and it's going to become more blue because copper ions are blue. And the concentration of the silver ions here are going to decrease because the mass of this guy is going to increase. The mass of it's going to go up because all that silver that's in the solution is going to turn into silver metal and plate onto it, which is just super cool. That's how you can kind of take the chemical energy and turn it into electrical energy and get this to actually run as a battery. So what you guys are going to do is you're going to do a simulation where you can pick the two metals that you've got, pick the solutions you've got, and you can actually see like what happens, where the electrons go. It's actually going to light up a bulb up here for you, which is cool. And you're going to be able to see on a molecular level what's happening at the anode and the cathode. So again, the anode is over here where oxidation is taking place, and the cathode is over here where reduction's taking place. So batteries are not all like built like this, but they're pretty much all a chemical reaction that's turning chemical energy, stored potential energy, into electrical energy. And then once that reaction hits equilibrium, which is something else that we learned about, once it hits equilibrium, your voltage or your current through the battery gets to be zero, right? Because your forward reaction rate equals your reverse reaction rate. And once that hits zero, then your battery's dead and you need to recharge it. Kind of like your phone, right? Like if my iPad here is going to lose battery soon because I just got a warning that it's under 10%. Once that's done, then I'm going to plug it into the wall and I'm going to force this reaction to run in reverse. And what that's called is an electrolytic cell. An electrolytic cell is a lot of this in the opposite direction, where I take electrical energy that I have and I supply, and I put it into chemical energy. And that's like charging your phone, using the electricity from your phone to make a non-spontaneous reaction, a reaction that's not going to automatically happen, so that then it can actually run in the other direction and give you that spontaneous electrical energy. So do the simulation. I hope that it'll make a little bit more sense to you. And you'll get an idea of like, this is some real cool application of chemistry and how we experience it regularly. All right, guys.